Okay, so in this video, we're going to talk about motion on an inclined plane or a ramp, which we've already looked at before. So this is just a brief review to help you with positive physics. And we already know that the acceleration of an object depends on the ramp angle. And we're going to explore why is this true. And to understand this, we really need to think about the forces acting on the object. And so, assuming that there's no friction, how would you draw a free body diagram for cart on the ramp? Okay, so we know that we've got the weight going down, and then hopefully none of you are persisting in your beliefs, but the normal force is perpendicular to the ramp, so it goes off in this direction, does not go straight up. And so that's what it looks like. And then remember, the velocity of the cart or the motion of the cart is in this direction, which means if we had normal coordinate system, that it would actually be moving in the x and y direction. And so in order to make this problem easier to solve, we tilt the axes in order to turn this into a one-dimensional motion problem. So remember, we did a lot of questions on this. We're actually going to make our axes go this way, and so our motion is only along this axis. And so we've got these. All right, so we know that the normal force and the gravitational force do not completely cancel out. Otherwise, the cart would not move, but it definitely accelerates along the ramp. And so I called this motion, or the coordinate, parallel and perpendicular, but it's just as easy to label them x and y. And so now my motion is only in the x direction. Okay. Now, we then have to convert weight into components that that align with my axes. And so I've got, this is the x component of the weight. So we've got weight x, and this one is the y component of the weight. When we have our axes tilted like this, and then mg is just equal to the weight. Now, if we look at the net force in the y direction, the forces that we have acting are, we have the normal force going up, and then we have a y component of the weight, and this is equal to 0 because there's no motion in the vertical direction. And so this tells me that my normal force is equal to just mg cos theta, because component of weight in the y direction is that. All right, if we look in the x direction, so net force in the x direction, and we look at our diagram, we only have weight in the x direction. But that is actually accelerating, and so that's going to be ma, and you can put x if you want to. And so what we end up with is that mg sine theta is equal to max. So this is what we have, F net. We've got mg sine theta is equal to ma. Those are both the mass of the cart, and so these masses cancel out, and so this is the acceleration of the cart down the ramp. It's something that's really important to remember is that this is assuming no friction. So what happens if there is friction? So that means I have another force in the x direction going backwards. And so I've got F net is going to be mg sine theta. So remember, this is our weight in the x direction going down the ramp, and then force of friction going up the ramp, and that's going to be max down the ramp. But I know that the force of friction is equal to mu times the normal force. And we already figured out that the normal force is equal to mg cosine of theta. And so I can make this a little bit more complex. So I've got mg sine theta minus mu mg cos theta is equal to max. And every single expression in here has an m. And so I can also find acceleration when there is friction. And so I've got an g sine theta minus mu g cos theta is equal to ax. So that's acceleration when there is friction. Okay, so we know that the acceleration of an object on a ramp depends on the ramp height or the ramp angle. And to really understand this, we need to think about the forces acting on the object. And so we know the acceleration is g sine theta. So what do we know about the value of sine as theta increases? Okay. So if we have just a flat surface with the cart on it, we know that theta is equal to 0 and sine theta is also equal to 0. Let's look at the other extreme. If instead we have a maximum angle, so here's my ramp, and here my angle is 90 degrees, so theta is equal to 90 degrees. We know that the sine of theta is equal to 1. So in this case, if I have A is equal to g sine theta, my acceleration due to gravity is 0, which is true, this cart's just going to stay here. For the other example, again, A is equal to g sine theta. This is just A equals g because sine of theta is 1. And this tells me that this cart is going to accelerate with just the same value as the acceleration due to gravity, which is true. It's just in free fall, okay? And so the idea is that sine is actually an increasing function. So we've got sine of theta, and theta over here, this is 0, this is 90. You know what a sine curve looks like. It goes like that. And so as the angle increases or goes from 0 to 90, the value of the sine of theta goes from 0 to 1. I should put that up here, 1. Okay, and so that's why the acceleration increases, because it's a function of sine. Okay, so I thought you might like having just a summary table of the equations that you will need for doing positive physics. So you might want to take a screenshot of this or stop the video and write these down. And then the other thing is that we are combining, once we know acceleration, then we can start figuring out displacement and velocity. So you might also want these equations at your fingertips.